In this video, I would like to discuss end of chapter question 3 from chapter 22 from the book Chemistry Cubed. And I will briefly read out the question. Benzocaine 5 is a local anesthetic which is formed from 4-amino benzoic acid, 4. First question, suggest a 3-step synthesis of 4 starting from toluene, and parentheses methylbenzene. Comment on the rigid selectivity of any electrophoretic substitution reactions. So we see our target molecule 4 here in the top left hand corner, and we need to start synthesizing this from toluene. So the first thing we can do is draw our intended starting material, and as the question points out, it's actually the methyl derivative of benzene. So we have methyl benzene here in this case, and we need to start synthesizing molecule 4. So I will also copy that over, and we can see we have our unsubstituted or on our just our monosubstituted benzene as a starting material, and in the end we end up with a par substituted benzene. So we have an amino group and a carboxylic acid here in this case. What we can see is that our starting material already has 7 carbon atoms, so 6 in the benzyl ring and 1 in the methyl group, and our target molecule also already has 7 carbon atoms, so we actually don't need to add any carbon atoms to our molecule. What we indeed need to add is this nitrogen atom here, so this is probably something that we would like to do, and we need to change the methyl group into a carboxylate somehow. So this is something where we probably want to oxidize the methyl group somehow. So what we first need to do to answer this question is to analyze maybe the directing effect of this already present methyl group here. And as we've discussed in the video lecture, methyl groups act as slightly activating 2 and 4 directors, so they actually push subsequent substitution reactions into the para or into the ortho position. And this is something that we actually can exploit in our synthesis because the amino group in our target molecule is actually in para position. So this is something that we can do. So the first step is somehow introducing a nitrogen-based substituent in para position, starting from our toluene. How can we do that? We can use the nitric acid together with sulfuric acid to do a nitration reaction. That would actually look something like this on the reaction conditions side. So the mixture of these 2 acids here, and this produces this NO2 plus ion that acts as an electrophile and then attacks. What we're actually getting is 2 molecules. I would just copy our toluene molecule. In the end, because we are having a substituent that pushes in 2 and 4 position, we probably get something where the substituent is in para position. That is actually what we want to do or want to have. And the other thing that we get is the substituent in ortho position. That's something that we do not desire, so we need to get rid of that through a separation step somehow. So these are our 2 first products that we are receiving, and we need to separate the ortho and the methyl product. We are barely getting any meta substituted product, and the few molecules from the meta substituted product that we also get will probably also need to be separated with this maybe with a distillation step. So and then we are left with this para-nitro toluene molecule after we have separated that out. And what we can do now is we first need to change our nitro group into an amino group, and we need to change the methyl group into a carboxyl group. And now the question is, how can we do this? The first answer is that we probably can oxidize the methyl group with, for example, potassium permanganate and oxidize from methyl to carboxylate group. This would then look something like this here. I will just add the reaction arrow in this way so that's clear that we are not using the ortho product, we are just separating that out. Reaction conditions might be, as I said initially, potassium permanganate is quite a strong oxidative agent, so this can oxidize our product here towards the desired carboxylic acid, and we would get something that looks like this here. And then in the next, or in the final reaction step, we actually need to reduce our nitro group to our amino group, and this can be done, for example, with tin in hydrochloric acid. One thing to remember here is that probably this reducing agent may also interact with our carboxylic acid group, because this can also again be reduced maybe to an aldehyde or an alcohol. And something that we can potentially do to circumvent that or to counteract this is introducing a protecting group onto our carboxylic acid. Don't want to talk about this too much now. This is just like one precaution measurement that we maybe need to do, and then after we've done the reduction step, we can remove this protecting group. Actually, what is also possible is exactly the other way around. First, reduce the nitro group to the amino group, and then protect the present amino group with like a protection group, and then use, for example, potassium permanganate to oxidize our methyl group here in the end. So in the end, the trick here is, or what is a little bit tricky, is that we are having one quite reduced group here. So the amino group has a low oxidation state, and the carboxyl group has a high oxidation state. So basically tuning the reactivity of these two groups in the same molecule is a little bit tricky, and here we might need to use this protection groups. Okay, this is the answer to the first question. And the answer to the regioselectivity is something that we've just discussed. It's the 2 and 4 directing influence of the methyl group. Next question from question 3 is, which position of the ring in benzocaine is most reactive towards an electrophile? Explain your reasoning by drawing resonance forms of the carbocationic reaction intermediates. So the benzocaine molecule is actually molecule 5 here, so it's the basically the drug. And I'm also copying this structure and bring this down here a bit so that we can work with a bit more space. And so the question is, where does an electrophile attack? First, let's maybe add an electrophile here somewhere that wants to attack. Maybe it's positively charged. And if this reacts now with our benzocaine molecule, we are having basically two positions, the 1 and the 4 positions. So vice versa are already occupied, so we're having just like this also positions relative to the amino group and the also positions relative to the carboxyl group, and of course this is the meta position relative to the amino group. And where can it attack, and which one is more stable is the question now. So let's draw the reaction intermediate first for the attack and auto position relative to the amino group. That would look something like this here, and I also add the present hydrogen atom in this case. And then we are getting our intermediary carbocation that also the question talks about. So this is the structure here that we would get in the case, in this first case here. And what we can see is now that this carbocation can actually be stabilized by the amino group, because the amino group, if I just add that here, has a lone pair, and this can now be used to stabilize this positive charge here by delocalizing the positive charge onto the amino atom by moving the lone pair at the nitrogen atom into the or onto the carbon nitrogen bond here in this case. We color this in red, and then we would actually get this resonance structure. So we are drawing the resonance arrow here in this case. I would just copy this molecule over here, remove the arrow, remove the lone pair, remove the cationic charge, add the double bond here, and then add the cationic charge now to the nitrogen overall. And then we are seeing that this structure is actually stabilized. The other intermediates look quite similar, and there we can also delocalize the positive charge onto the para position relative to the point of the attack and onto the other also positions. I will also quickly draw them out now without always showing the electron density, because this takes a lot of time to draw in a nice way. So this would look something like this, and the other intermediate where it's in also position is actually something that looks like this molecule here, but the positive charge is now here. So this is actually quite nice. We just add the resonance arrows here to make it complete. So all of these structures contribute to the stability. So this is actually very good. That are the resonance structures for the auto-substituted product here. And now let's have a look for the attack in meta position relative to the amino group. Just draw the reaction arrow here, copy our molecule, and then add the electrophile to the molecule so that you can see how it adds this electrophile and why this is actually less stabilized with the help of the amino group. And here we're adding the electrophile and positive charge here now onto the carboxylate or on the ipso carbon atom of the carboxylate group. And yeah, now we can draw the resonance structures, and actually there's no way that we can somehow introduce the lone pair of the nitrogen atom into this resonance structure. So we can only delocalize this positive charge of this carbocationic intermediate inside the carbon ring, but not onto the amino group. And this actually is then one resonance structure less, so it's not as stable as the other alternative. I will just quickly draw that here. And this then in the first place looks something like this. So this is now in power position to the point of attack of the electrophile, and the other intermediate then looks similar, but the positive charge is now in auto position relative to the point of attack. And what we cannot do is, I can try now, but this will not be possible. So let me somehow do this. Maybe just have the positive charge present here. If I want to now somehow push this lone pair into here or get the positive charge onto the nitrogen, that's not possible, because for the positive charge to go into the nitrogen, it needs actually to be located on the carbon atom where the amino group is directly attached to, as we've seen here in this case. Here in this case, the amino group can help stabilize it, and in this case here, for the attack and meta position to the amino group, this is not possible. So actually, there's no way that I can draw this resonance structure here, so I just delete this, and then you can easily count. So this is one way of actually finding out if something is more stable or not, or which intermediate is more stable, by counting the number of resonance structures that you can draw. And here in this case we can only draw 3, 1, 2, 3, and for the other case with the amino group involved, we can actually draw 4, and this is something where we can conclude from that this attack actually is favored in the auto position relative to the amino group. And actually the same thing happens here with the carboxylate group. You can also draw this out, is that the carboxylate group is now a 3-directing group, so it actually pushes the substituent or subsequent substituent into the meta position, and this is actually then also the case for this point of attack, because it's in meta position, and here in the second case we discussed the electrophile attacks in the auto position relative to the carboxylate group, and it's also not favorable in this way. So overall, this is the solution to this question. Last question is, would you expect benzocaine 5 or component 6 to react more rapidly with an electrophile? Explain your reasoning. Let's scroll up to our original reaction scheme, and we see here benzocaine 5 and the other structure 6. So we are seeing that in this case, in structure 6, our amino group got a newly added acetyl group. And the question is now, which of these reacts faster with an electrophile? And the answer is that probably the benzocaine would react more rapidly with an electrophile. Why is that? The amino group, like the pure amino group that's not protected somehow or not reacted with something else, is actually a stronger plus M substituent, because the lone pair is more available. It also has more electron density because it has 2 protons attached, and they can then also help to push electron density into the ring. In the other case, with the acetyl group, we can also draw a resonance structure where the lone pair is partially located onto the carbon-nitrogen bond on the other side. I will quickly draw that here for use. And something that we can then see is that we can locate this here. Of course, we need to get rid of that. And then we get basically partially this structure. Doesn't look ideal. So like this. And the negative charge on the oxygen atom. So this is another partial structure here that's also typical for amides. And then we see that the lone pair of the nitrogen also gets delocalized into this direction, and so it's less available for the benzene ring. So this is the reason why the benzocaine would actually react more rapidly with an electrophile. Another reason that I would like to point out is now the steric hindrance induced by this acetyl group here. The acetyl group is somewhat bulky, so it's definitely more bulky than just a proton attached to the nitrogen. And as we've discussed just before in the second question, the electrophilic attack would like to happen here in the ortho position. And this position here is now also sterically shielded somehow to some degree with the acetyl group. And this is then actually also another reason that the electrophile would react less rapidly, because either it can go into the meta position relative to this substituted amino group, and that's not so likely to happen, and in ortho position it experiences some steric hindrance, so this is also not very likely to happen. So overall, the benzocaine would react faster, first for electronic reasons, and second also for steric reasons.